HANYCO produces up to 2,000 tons of ductile iron fittings annually using the lost foam casting LFC method, a modern, efficient, and environmentally friendly process. This method involves creating a polystyrene model of the desired fitting using precision aluminum molds and autoclave systems. The model is coated with refractory material and dried, then placed in a flask filled with unbonded sand. During casting, molten metal is poured into the flask, vaporizing the foam model and replacing it with solid metal. This method enables the production of highly detailed and complex parts with minimal machining. All fittings are manufactured in strict accordance with ISO 2531 and EN 545 standards, ensuring global compliance for water and sewage applications. HANYCO's production line includes one 12-ton and four 5-ton induction furnaces. After melting, the molten iron is transferred to a 30-ton holder furnace for temperature control and composition analysis. The magnesium treatment, which gives the iron its ductility, is applied using either the cord wire method or the sandwich method. The company also uses centrifugal casting machines for pipe and lighting pole production, utilizing cold box method cores that are precisely marked with identification codes, ensuring full traceability and quality control. At HANYCO, the entire pipe production process is highly automated and integrated with advanced quality control systems to ensure precision, durability, and compliance with international standards. All operations are carried out using centrifugal casting machines, which allow for the consistent and uniform formation of ductile iron pipes and lighting poles. These machines function with minimal manual intervention, improving both efficiency and product uniformity. The production line is equipped with a Manufacturing Execution System, MES, a digital platform that precisely monitors and manages each stage of the production process. Through MES, every pipe is assigned a unique production ID, enabling full traceability from raw material to final product. Following casting, the pipes undergo an annealing treatment in a horizontal tunneling furnace. This heat treatment process is critical in modifying the microstructure of the cast material. Specifically, it dissolves residual carbides and promotes the nodulation of graphite within the iron matrix. These changes significantly enhance the ductility of the pipes, which is essential for withstanding internal pressure and external mechanical stresses in water distribution systems. After annealing, the outer surface of each pipe is subjected to a zinc coating process using the plasma spray method. This galvanization step ensures a minimum zinc layer thickness of 200 grams per square meter and significantly increases the pipe's resistance to corrosion. This layer functions through a mechanism known as sacrificial protection, where zinc corrodes preferentially, thereby shielding the underlying iron. Once galvanized, pipes are directed to the hydrotest station, where each one is subjected to a non-destructive pressure test to detect any potential cracks or leaks. Hydrostatic testing is conducted at various pressures, up to 53 bars, depending on the pipe's diameter, wall thickness, and classification. Lighting poles, which do not carry pressurized fluids, bypass this step and move directly to the paint workshop. Dimensional checks and visual inspections are performed throughout the production stages in accordance with ISO and EN standards. The inner surface of each pipe is coated with a 2 mm layer of cement mortar using the centrifugal method. This internal lining ensures hygienic water conveyance, reduces surface roughness, and facilitates smoother, laminar fluid flow. The pipes are then transferred to a curing chamber, where they are maintained at temperatures between 55 degrees Celsius to 75 degrees Celsius for at least 14 hours to allow complete cement hydration and bonding, ensuring structural integrity and performance longevity. In the final stage of production, a bituminous paint is applied to the outer surface of the pipes, providing an additional protective layer against environmental factors such as moisture, soil chemicals, and physical wear. This coating is sprayed uniformly to achieve a minimum thickness of 70 microns, ensuring long-term durability and corrosion resistance, particularly during transportation and underground installation. Once coated, the pipes are transferred to a temperature-controlled drying room to allow the bitumen to cure and adhere properly. After drying, an automatic marking system labels each pipe with essential information such as size, standard, batch number, and production date. The fully processed and labeled pipes are then transported to the storehouse unit, ready for packaging and shipment to domestic or international customers. The creation of a Tadano rough terrain crane is a carefully orchestrated process that blends engineering excellence, advanced manufacturing, and rigorous testing to ensure superior quality and performance. It all begins with design and planning. Engineers at Tadano analyze global market needs and job site requirements to conceptualize a crane that balances power, compactness, and ease of operation. Using 3D CAD software and simulation tools, they fine-tune every detail, from boom structure to hydraulic systems, to meet high standards of safety, mobility, and efficiency. Once the design is finalized, production moves to component manufacturing and assembly. Key parts such as the chassis, boom, and outriggers are fabricated with precision. Tadano emphasizes quality control throughout, using robotic welding, CNC machining, and automated processes to ensure consistency. The crane's powerful engine and advanced hydraulic systems are integrated, followed by installation of electronic control units and sensors that support smooth operation and safety features. Next is assembly and integration, where the crane begins to take shape. Skilled technicians assemble major sections, like the carrier, upper structure, and boom, on the production line. Electrical wiring, hydraulic lines, and software systems are carefully connected and configured. The entire machine is then subjected to comprehensive calibration to ensure all functions operate seamlessly. Finally, each crane undergoes strict inspection and testing. This includes load testing, function checks, and real-world operational simulations to verify lifting capacity, maneuverability, and safety systems. Any adjustments needed are made before the crane is approved for delivery. The result is a rugged, high-performance machine capable of operating in challenging environments, construction sites with limited space or rough terrain. Tadano's rough terrain cranes are not only used across Japan, but are also trusted worldwide for their durability, ease of use, and advanced engineering. Raw material section stores and handles cement, aggregates, water, and steel, ensuring quality control before batching and production processes. The batching plant precisely measures and mixes raw materials such as cement, sand, aggregates, water, and additives to produce high-quality concrete. It ensures consistent mix designs for various production needs, including precast and spun piles. Automation and control systems help maintain accuracy, efficiency, and quality throughout the mixing process. The precast drainage section manufactures concrete drainage components like U-ditches, box culverts, and manholes using standardized molds. Concrete from the batching plant is poured into these molds, then cured to achieve strength and durability. This process ensures consistent quality, dimensional accuracy, and efficient production for infrastructure and civil drainage systems. Spun production is a specialized manufacturing process used to produce high-strength, circular concrete piles, known as spun piles. The process begins with assembling pre-stressed steel wires or strands inside a cylindrical mold. Once in place, high-quality concrete from the batching plant is poured into the mold. The mold is then rotated at high speed in a spinning machine, using centrifugal force to compact the concrete and remove excess water, resulting in a dense, durable product with excellent load-bearing capacity and resistance to cracking. After spinning, the pile undergoes steam curing to accelerate the hardening process and achieve the required strength in a shorter time. Once curing is complete, the pile is demolded and moved to the finishing and storage area. Spun piles are widely used in foundation works, especially in challenging soil conditions, due to their strength, uniformity, and precision. Quality control is strictly maintained throughout each stage to ensure compliance with structural standards. Solid production involves the manufacturing of non-spun, solid square or rectangular, pre-stressed concrete piles used primarily for foundation works. The process starts by preparing molds and placing pre-stressed steel tendons along their length. High-quality concrete is then poured into the molds and compacted, using vibration to eliminate air pockets and ensure density. After pouring, the molds are transferred to a curing area, often using steam curing to accelerate strength gain. Once the concrete reaches the required strength, the piles are demolded, cut to the desired length, and finished as needed. Solid piles are known for their robust structural integrity and are commonly used in building foundations, retaining walls, and infrastructure projects. METALPOL is a premier steel pole manufacturer headquartered in Gómez Palacio, Durango, Mexico. Strategically located in the heart of northern Mexico, METALPOL benefits from its central position in the metropolitan area known as La Comarca Lagunera, which includes the cities of Gómez Palacio and Lerdo in Durango and Torreón in Coahuila. This region, with a combined population of approximately 1.375 million people, is a vital industrial hub that supports METALPOL's efficient operations and skilled workforce. Just 367 miles from the U.S. border city of Laredo, Texas, the company enjoys excellent logistical access to North America. Approximately 70% of METALPOL's steel pole products are exported to the United States and Canada, while the remaining 30% are distributed across Mexico, Central America, and South America. This strong presence in both North and Latin America highlights the company's role as a key player in the regional steel infrastructure sector. METALPOL's mission is grounded in three core principles: delivering high-quality products with exceptional service, achieving full satisfaction for both clients and employees and their families, and maintaining operational efficiency to support competitive pricing and profitability. These guiding values have positioned the company as a trusted partner for customers seeking durable, reliable steel pole solutions. A cornerstone of METALPOL's success is its commitment to quality assurance. The company employs a rigorous quality control system that includes a certified welding inspector, CWI, accredited by the American Welding Society, AWS. Furthermore, METALPOL's inspection team includes Level 2 specialists in non-destructive testing, NDT, trained in techniques such as ultrasonic testing, UT, magnetic testing, MT, and penetrant testing, PT. These inspectors are qualified according to the standards set by the American Society for Non-Destructive Testing, ASNT, under the SNTT C1A recommended practice. All welding procedures and personnel at METALPOL are fully certified to ensure compliance with industry standards and guarantee product integrity. At voestalpine Stahl Donawitz, the steel production process is centered on creating high-performance steels, tailored for demanding industries such as railway infrastructure, automotive manufacturing, and oil and gas, e.g. deep drilling pipes. The production process begins with primary steelmaking in a blast furnace, where raw materials such as iron ore, coke, and limestone are heated to produce molten iron. This molten iron then undergoes the LD Linz-Donawitz process, a method that uses oxygen to reduce the carbon content, converting it into high-quality steel. From here, the steel moves into secondary metallurgy, where advanced processes such as vacuum treatment are used to refine its chemical composition and purity, ensuring the lowest possible content of impurities like sulfur and hydrogen. This step is crucial for producing steel that can withstand high stresses, which is essential for applications like high-speed rail, automotive safety components, and deep drilling pipes. One of the standout features of voestalpine Stahl Donawitz is its ability to produce ultra-long rails, measuring up to 120 meters in a single cast. This process minimizes the need for joints and ensures that the rails are highly durable, capable of withstanding the extreme conditions encountered on high-speed rail networks. The production of these rails is made possible by the company's optimal steel casting technology at Donawitz, allowing for efficient production with short lead times and reduced transportation distances. For the automotive industry, voestalpine Stahl Donawitz focuses on creating steel grades that meet specific demands for vehicle safety and performance. The steels are designed with low sulfur content and high purity, which results in materials with superior strength and formability. These properties are essential for producing high-strength steel components used in critical automotive parts like body panels, chassis, and engine components. In the oil and gas industry, the company produces high-performance steel for deep drilling pipes. The steel's resilience is critical for the harsh conditions encountered in deep drilling, where materials must endure extreme pressures and temperatures. The journey begins at the scrapyard, where iron scrap is collected and stored in a large, designated area. This scrap, which is the primary raw material, undergoes a critical radiation inspection to ensure there are no harmful contaminants before being admitted to the production line. Specialized vehicles transport the scrap to the storage areas within the plant. Once inside, the scrap is sorted and classified into different categories based on density and chemical composition. After sorting, the clean scrap is loaded into specially designed baskets using overhead cranes equipped with electromagnets or grabs. These baskets are then transported on rail-guided trolleys that have built-in weight sensors, ensuring each charge is accurately measured. The baskets are delivered to the electric arc furnace, EAF, where the actual melting takes place. This furnace, located in the melt shop, uses 3 high-power electrodes to generate a 3-phase electric arc, which heats the scrap to extreme temperatures. The EAF at Hadeed operates at a power level of up to 70 megawatts, enabling it to raise the scrap temperature by approximately 50 degrees Celsius per minute until complete melting occurs. Each melting cycle consists of multiple scrap charges, with an average melt weight of 90 tons and a total cycle time of about 50 minutes. During melting, impurities and oxides separate from the molten steel and rise to the surface as slag. This slag is removed through a specially designed side outlet below the furnace. It is then collected, cooled, and often recycled. A sample of the molten steel is taken using an automated sampling system to measure temperature and carbon content. Based on this analysis, additives like lime and carbon are introduced. Additionally, gases are injected through 6 tuyères, gas inlets, around the furnace to aid in refining the molten steel and achieving the desired composition. Once the initial melting is complete, the molten steel is transferred to a ladle furnace LF, where precise chemical tuning is performed. The ladle is preheated using gas burners, and further additives are introduced to bring the steel's composition in line with international specifications. The ladle furnace process includes the automatic and periodic collection of samples. These samples are sent to a modern, in-house laboratory equipped with the latest technology. The results are used to make final adjustments to the composition before the steel moves to the next stage. With laboratory approval, the molten steel is moved via crane to the continuous casting machine, CCM. Here, the steel is poured into casting molds, where it begins to solidify into billets. This process is highly automated and controlled by an advanced computer system to ensure consistency and precision. The casting molds are inspected for quality and structural integrity, and thermal insulation materials are checked to avoid any heat loss or casting defects. The continuous casting process allows for high-speed solidification, enabling the production line to respond quickly to market demands. Hadeed's CCM has a casting radius that supports various billet sizes, typically ranging from 100 times 100 millimeters to 120 times 120 millimeters, with lengths between 6 to 12 meters. The billets are usually cut to 12 meters using flame torches, although different lengths can be produced as per customer requirements. As the billets cool, their color shifts from glowing red to black. Once solidified, billets are transferred using overhead cranes fitted with electromagnets to the storage area, where they are neatly arranged and labeled. Each billet batch is tagged with unique identifiers to differentiate between production runs. From here, billets are loaded onto trucks for delivery to customers. The entire loading process is documented. Incoming trucks are weighed empty, and then again, after loading using calibrated electronic weighbridges, inspected regularly by government authorities to ensure accuracy. Hadeed prioritizes environmental sustainability by installing advanced fume extraction and filtration systems that treat all emissions before they are released into the atmosphere, ensuring compliance with global environmental standards. The plant also includes a water treatment facility that improves production quality and helps conserve water through recycling. Additionally, an industrial gas plant separates gases from the atmosphere and supplies the factory with oxygen, argon, and nitrogen in both liquid and gaseous forms. Any surplus gas is sold to external markets. A liquefied gas station supplies fuel for the production processes, adhering to international safety and quality standards. Power is delivered via an in-house 15 MVA substation equipped with SVC static VAR compensator technology to enhance energy efficiency and reduce reactive power losses. The facility has a production capacity of up to 800,000 tons per year and utilizes cutting-edge Italian technology provided by Danieli, a global leader in steel production equipment.